are congruent. Angles 9 and angle 12 are congruent. Angle 10 and 11, they're also congruent. Angle 14 and 15 are congruent. Whoa, my congruent symbol doesn't look so good. See if it erases eventually. Come on. There we go. It had to think about it. Let's see if I can do that better. And I'll take it. And finally, angle 13 and angle 16 are congruent. Why are all those pairs of angles congruent? Well, those angles are vertical angles. Some things we learned about vertical angles. They're formed by two intersecting lines. They share a vertex. They're opposite one another. And, very important, they're always congruent. Let's take a look at some angles that are not congruent. So, for instance, angle 9 is not congruent to angle 10. And angle, angle 13 is not congruent to angle 15. And angle 11 is not congruent to angle 12. None of those angles are congruent. What is true, angle 9 plus angle 10, angle 13 plus angle 15, angle 11 plus angle 12, they all add to 180 degrees. Those angles are linear pair angles. And let's talk about linear pair angles. We learned in the last lesson that linear pair angles also formed, let me rewrite that a little nicer. Looks like it's written in another language. When I'm writing, I can't see the words go up until after they're there. So linear pair angles are also formed by two intersecting lines. They're adjacent. Right, so that means they're next to one another. And very important, they are always supplementary, which means they add to 180 degrees. Now, can linear pair angles ever be congruent to one another? Well, yes. If those linear pair angles are both 90 degrees, right? 90 plus 90 would add to 180, and then they'd also be congruent. But we have no reason to believe that these are right angles. There's no markings to tell us they're right angles. So we are right to assume, that I need to put that line in there, that these are not congruent angles. Hey, where's my line? There it goes. Not congruent angles. but you couldn't see it because it didn't shine. There it goes. There it goes. That arrow there tells us something about our lines. It tells us that line M is parallel to line N. And because those lines are parallel, it tells us some other things about these angles that we're going to learn about in upcoming lessons. I don't know if you noticed, but I put the same number of arcs on 9, 12, 13, and 16. And actually, those angles, they are all congruent to one another. I also put the same number of arcs on angles 10, 11, 14, and 15. And those angles are also congruent to one another. One other thing before we go on, notice that I named the lines with a single letter. We can do that when a line is labeled with a single letter. Right? And when it's labeled with a single letter, it will be a lowercase letter, usually written in italics. Don't ever name a line with a letter that's a point. Right? We need 2 points to name a line, but if a line is labeled with a letter, we can use that label instead. Right? So we're going to learn a little bit of kind of a fancy angles and lines and other things in mathematics and geometry that we could use to prove something's true. Sometimes we'll be given information in a picture. Notice that I knew those 2 lines were parallel to one another because of the picture. The picture shows me the lines are parallel. We can also use the picture to show us that, for instance, angles 9 and 12 are vertical angles. We can see they're clearly formed by 2 lines, that they are opposite one another, and therefore are vertical angles. And we know that vertical angles are always congruent. So sometimes we'll be given information from a picture. Sometimes we'll be given information, that's written information. We'll be told something, in other words. Right? We'll be told something is true. And when we know one thing is true, we'll know other things are true as well. We just have to properly justify why these other things are true. So for instance, we knew that angles 9 and 12 were congruent to one another. We have to justify why that's true. It's true because they're vertical angles. Right? So these angles are all congruent because they're vertical angles. Oh, can I fit it all in? Yes. Oh, I fit it all in. Right? So because they're vertical angles, we know they have to be congruent to one another. Right? So we're always going to, in mathematics, we're always going to justify why we say something is so. Right? We're never going to be like, because I said it's so. No. We're going to say why. Right? Let's look a little introduction to math proofs. And my next page, there we go. So in math, we use proofs to demonstrate a statement or something we've discovered is true. Everything that's ever said in math is always true. We never say anything that we haven't proven to be true. If it's just something we think is true, but we haven't proven to be true, then we say we have an hypothesis, we think it might be, but we never say it's true. So anything that we say in mathematics has been proven to be true. That's why it's the queen of all sciences. We use different theorems and properties to make our point. So here I have a number statement. 24 times 21 equals 42 times 12. And my question for you is this a true statement? Well, one way we can find out is by multiplying, right? Let's find out. All right, so if I take 24 times 12, oops, I reversed my numbers there. 24 times 12. Oops, I'm sorry, 24 times 21. I was writing the right thing the first time. 24 times 21. Sometimes when I'm looking sideways, I actually read it backwards. And 42 times 12. There we go. Now I got the numbers written down right. Let's take those two products and find out what they equal. All right, so I've got 24 times 1, that would be 24. And then I have 24 times, that 2 there means 20. All right, so 24 times 20 is going to be 480. It's just 48 with a 0, right? 24 times 2 with a 0. If I add those together, that's going to give us 504. If you notice, I tend to multiply, add, and subtract a lot of times. Well, not so much subtraction, but multiply and add left to right instead of right to left, and that's just because I'm chunking the numbers together in my head. And you can do that too. It's just practice. It's no special gift I have. All right, so 42 times 2, that's going to be 84, right? Just twice as much. And 42, that 1 means 10. 42 times 10, it would be 420. So we add those together, that's going to be 504. Notice it's the same. Well, why is it the same? Is it because, and if you notice, we got 24 and then we switched the numbers for 42, and then we have 21, which I kept trying to switch for 12, but 21, and then we switch it, we have 12. Huh. Would that work with any pair of numbers? Now, just because something works once doesn't prove it to be true. Matter of fact, just because something works 100 times doesn't prove it to be true. We'd have to know it worked all the time. But let's see if it would work again. I'm just going to pick any number. And I'd ask you for numbers, but I can't hear you, so I'll just pick some random numbers. All right, I'm just going to pick, 63. So that means this one would be 36. And how about 14? And this one would be 41, right? So I've got two pairs of numbers. I reversed them. All right, let's try multiplying them, see what we get. So I got 63 times 14. This was not as easy for me to do in my head. 63 times, because I have 63 times 4. It was a lot easier doing 24 times 1 and 42 times 2. All right, so 63 times 4, that's going to be, so I'm going to actually do this in order you're used to, right to left. So that would be 25. Right? And then 63, that would be times 10, that would be 630. All right, so add those together, and somehow I've run out of space. Seems like my board seems short today. I don't know how. All right, so if I add those together, I have, this is going to be 8 and another 8, so 8, 8, 2. Well, come on. And it decided to extend. It really does look shorter. I don't know, I'm not used to seeing stuff on the bottom there. I don't know what I did to make the board shorter, but somehow I did something. Maybe I need to move it down a little bit. All right, so let's multiply the other pair there. 36, I'm gonna try to write shorter, so write smaller, so I don't cause the board to extend. All right, so now 36 times that times 1, that would be 36. 36, now I got 36 times 40, right? So that's going to be, and then that would be 100, that'd be 14, right? So 36 times 40 would be 1,440. And you can check my math. You can tell me if I make a mistake. I'm not perfect. All right, so now 882, that's definitely not 1,476. Matter of fact, if we just looked at the first digit, 3 times 4, that's going to be 12, it's going to be a 2. 6 times 1, that's going to be a 6. I could have stopped there to tell that they're not the same. Right? So clearly it has nothing to do with the switching of numbers. I'm going to move these numbers up above. Let's write down some things that we know about numbers and multiplying them. And I'm going to write a statement. Actually, I'm going to fix my red statement here, the one I'm just moving up here. So we have an equals next to 24 times 21 equals 42 times 12, because that was true. But that was definitely not true. So let's write down some things we know. Well, first of all, multiplication is what's called commutative. I like to use the right terminology so that you learn the terminology. So multiplication is commutative. What does that mean? That means the order you multiply doesn't matter. Order you multiply is what I was trying to write, and then I started to write multiplication for some reason, which is not a very good sentence. So the order you multiply in doesn't matter. That's also true for addition. All right, so if I add 3 plus 4 or 4 plus 3, it's going to be 7 either way. If I multiply 2 times 5 or 5 times 2, that's 10 either way, right? So the order I have numbers in doesn't matter when I'm multiplying. Other thing we know is we can break numbers. When I say break numbers, I mean divide numbers. Into prime factors. So break numbers is not math terminology. That's just my own language. But divide numbers is. So we're going to break numbers or divide numbers into prime and prime factors. Right, so we can just rewrite them as a product of the factors. And I'm actually going to write it that what I just said, because I actually like what I just said better than what I wrote. I'm a mathematician, not an English major. All right, so we can rewrite numbers as products of other factors. Although the other part kind of helped explain this. Of their factors. We're going to break it into prime factors. All right, so let's take this 24 and 12, and if I can find some itty bitty bit amount of space here, I'll put it over here. All right, so 24, and you can pick. You'll get the same factors no matter what number you choose first. Let's just take 4 and 6. All right, so 4 is not prime. I can divide that into 2 and 2, and 6 is not prime. I can divide that into 2 and 3. Now what if I had chosen 8 and 3? Would I get the same numbers? Well, 8 is just 2 times 2 times 2, and then we'd have a 3. So you see, it really doesn't matter what numbers I choose to start with. I'm going to get the same factors no matter what. Let's do the same thing with 21. Right, so 21, well, that's 7 and 3. That's their prime factors. And there are no others. Those are prime numbers. 42 is 6 times 7. 7 is prime. 6 is 3 times 2. And last, 12. I can do 3 and 4 or 2 and 6. Let's do 2 and 6. And of course 6 is 2 times 3. All right, so now if I look here, we have 1, 2, 3, 2. So I'm looking at, whoops, well, I don't know how I did that. I didn't even come close to the bottom of the board. And somehow I made the board extend a whole lot of times, making this very, very small. And actually there's only one way I can undo that. Well, first of all, I have to get rid of this. And second of all, I'm going to have to go back to my previous page and go forwards. And there we go. Makes big again. All right, so we have the two pairs there, right? The 24 and 21 and the 42 and 12. So notice here I've got a 2, a 2, and a 2. I've got 2 times 2 times 2. I'll write that up somewhere, up here I guess. So 24 times 21 is 2 times 2 times 2. And look at that. We have 1, 2, 3 2's there too. All right, so for 42 and 12, is also 2 times 2 times 2. And if we have 2 3's, and I have 2 3's over here as well. What happened? Oh, one of them got lost. Come back, 3. He was right here. There we go. 2 3's. All right, so that's going to give us 3 times 3 for both of them. And notice we also have, each one has a 7. Whoops. There we go. So 24 times 21 and 42 times 12 is 2 times 2 times 2 times 3 times 3 times 7. So matter of fact, I could take two other numbers so long as I used up all of those factors. So for instance, if I took 8, and is that 2 times 2 times 2 would be 8, and if I took 3 times 3 times 7, that would be 9 times 7, or 63. So 8 times 63 would also be equal to all of these, because I'd be using the very same factors. So it just happens to work out that they happen to look like they're flipped numbers, but really the reason this works out is because they're just products of the exact same factors, right? Just grouped in different ways, but still using the same factors, right? So when we're completing proofs, we're going to prove things to be true. We're going to use properties that we know. For instance, I use the commutative property, and I also use the fact that numbers can be rewritten as product of their factors. It's actually called, just for a little background knowledge, this part here is actually what's called the fundamental theorem of arithmetic. How about that? You get some advanced knowledge there. Well, thanks for watching this podcast. In the next podcast, we're going to be learning lots of different theorems and properties and definitions that we can use in our proofs. And I'm going to put a little arrow here to show you that's the fundamental theorem of arithmetic. I think before I post this page, though, well, you'll see it like this on the video. Before I post this lesson, I think I'm going to make those numbers so much neater. Somehow we got a little crammed in here. But thanks for watching.